in Guizhou in China.
Well, the bridge slashes travel time across a deep canyon from 2 hours to just 2 minutes. And this is after 3 years of construction. Take a look at this report.
Imagine building a structure so massive, so technologically complex, that it fundamentally rewrites everything we know about modern engineering and human capability. Right now, stretching deep across thousands of meters of treacherous, open ocean currents, China has finalized its most heavily guarded, highly advanced mega project yet, a combined deep-sea bridge and submerged mega-tunnel system. Today, we go completely behind the scenes to uncover the secret technologies, custom-built robotic machines, and unprecedented structural breakthroughs that allowed engineers to build the absolute impossible.
No injuries have been reported, but the collapse is raising urgent questions about safety and construction standards in one of China.
2. Breaking the structural barriers, the sites and volatile marine challenges. To fully comprehend why this project was considered a mathematical and engineering nightmare, we must first look at the extreme environment where it was constructed. Building over open water is challenging enough, but constructing a 5,000-meter marine bridge corridor combined with a deep-sea island tunnel system requires fighting against the most volatile oceanic conditions on Earth. The project spans across a region that is hit by devastating Category 5 super typhoons multiple times every single year. The structure had to be engineered to withstand wind speeds exceeding 300 kilometers per hour, alongside massive, multi-directional tidal waves crashing continuously against its pillars. But the weather wasn't the biggest problem. The entire marine highway sits directly on top of highly unstable underwater fault lines, meaning the entire system had to possess built-in flexibility to absorb massive seismic activity without cracking or collapsing into the sea. Additionally, this exact stretch of water serves as one of the busiest global maritime shipping channels on the planet, with hundreds of ultra-large cargo ships, heavy container vessels, and oil tankers passing through daily. Designers could not simply build a standard low-hanging bridge across the entire stretch because it would completely block international trade routes. Elevating the entire bridge to unprecedented heights was also ruled out because the area sits directly in the flight paths of major international airports, creating strict altitude limitations for any towers or suspension cables. The only viable solution left was a radical, highly dangerous architectural hybrid concept, a transition from an elevated sea bridge directly into a massive, deep-sea submerged tunnel system connected seamlessly by engineered artificial islands out in the middle of the ocean. No country had ever attempted to execute this combination at this specific scale, with these exact environmental pressures, making it a clean slate for brand new technological innovation. The geologic profile alone required massive pre-construction mapping arrays. Engineers spent months deploying underwater automated surveying crafts to scan every square meter of the seabed floor. Shifting silt, loose mud, and massive trenches meant standard marine piling would fail within months. The columns had to penetrate deeper than ever before, locking into the bedrock beneath layers of ancient sediment. Furthermore, the environmental preservation of local marine life added an immense layer of difficulty. The waters are a protected habitat for rare species, meaning heavy chemical leaks, excessive acoustic noise from construction, or massive seabed disruption would shut down the entire initiative. The engineering teams had to invent entirely new, low-noise, non-extrusive drilling methods and fully sealed operational frameworks to satisfy strict environmental protection laws. This shifted the project from a standard construction job to an elite scientific expedition, requiring thousands of patents to be filed before the first concrete foundation could even be mixed. 3. Exclusive robotics and custom-built heavy-duty mega machines. Building this impossible structure manually out on the open sea would have taken decades and cost thousands of lives. To overcome this, Chinese engineering groups completely eliminated traditional on-site construction methods, replacing them with advanced automation, deep-sea robotics, and custom mega machines that have never been filmed or analyzed on other channels. The entire bridge was essentially built inside highly controlled automated factories on land and then assembled on water like a giant hyper-precise puzzle. By converting a marine construction site into a modular factory assembly system, engineers minimized the time spent exposed to unpredictable ocean weather. Inside these automated smart factories on land, massive steel girders and concrete deck spans were fabricated using fully computerized laser welding robots. These robotic arms utilized artificial intelligence to inspect every single weld line down to the microscopic level, ensuring zero structural defects. Once these multi-thousand-ton bridge sections were finalized, they were loaded onto custom-built heavy-lift transport vessels. These were not typical transport boats. They were equipped with complex dynamic positioning technology, driven by multi-directional thrusters linked directly to satellite constellations. This system allowed the vessels to counteract the continuous push of ocean currents, remaining completely stationary within a few millimeters of accuracy while out in deep water. The true star of the installation phase was a newly designed, custom-built floating crane vessel of unprecedented scale. This mechanical beast featured dual lifting booms capable of raising over 12,000 tons simultaneously. It would gently lift a fully prefabricated bridge segment, carry it above the pre-installed concrete marine pillars, and use computerized laser guidance arrays to line up the locking joints. This minimized the manual labor required on the open water to near zero. Humans were no longer setting bolts in dangerous storm conditions. Instead, engineers sat in climate-controlled control rooms, monitoring telemetry screens, as automated hydraulic jacks locked the segments together with seamless accuracy. For the underwater piling work, standard maritime drills were completely inadequate for boring into the dense deep-sea bedrock. Chinese developers engineered a specialized fleet of robotic seafloor drilling rovers. These heavy-tracked units were lowered directly to the seabed floor, operating completely autonomously via deep-sea umbilical cables. Equipped with ultra-hard diamond-tipped rotary drill heads and high-frequency acoustic scanners, these rovers bored deep shafts directly into the bedrock while continuously calculating soil density changes. If the machine hit an unexpected subterranean void or shifting sand pocket, its onboard artificial intelligence instantly modified the torque, rotational speed, and drilling fluid pressure to prevent a collapse of the shaft wall. This revolutionary automation increased piling speed by over 400% while maintaining an unblemished structural safety record. 4. The architectural marvel of rapid artificial island construction. The most critical and terrifying phase of the entire project was creating the transition points, the exact locations where the open-air sea bridge descends deep underwater into the dark abyss of the submerged tunnel. To achieve this safely, engineers had to build two massive artificial islands out in the deep ocean, functioning as heavy-duty structural anchors and transition hubs. Traditionally, building an artificial island takes years because it requires dumping millions of tons of loose rock and sand onto the ocean floor, waiting for it to settle, and slowly building it upward while fighting corrosive waves. Doing so in this location would have completely blocked international shipping lanes for months, an economic disaster that trade authorities could not accept. To solve this timeline crisis, Chinese civil engineers pioneered a revolutionary rapid island building technology that shocked global architectural circles. Instead of building from the bottom up with loose stones, they decided to drive giant hollow steel cylinders directly into the seabed floor to create an instantaneous outer retaining wall. Each of these massive steel cylinders stood over 50 meters tall, matching the height of a 15-story residential skyscraper, and weighed upwards of 550 tons. They were manufactured in specialized steel mills on land and transported to the oceanic coordinates via massive crane barges. Using an ultra-powerful array of synchronized hydraulic vibratory hammers, 12 of these massive industrial hammers were linked together onto a single control computer and placed on top of the steel cylinder. When activated, they vibrated the massive cylinder at precise harmonic frequencies, causing the surrounding ocean sand to behave like a fluid. Under its own immense weight and the high-frequency vibration, the 15-story steel structure would sink deep into the hard seabed floor in a matter of mere hours. A total of over 120 of these giant cylinders were driven into the ocean bed side by side, forming a massive, continuous circular wall out in the open ocean. Once the perimeter was securely locked, high-powered automated suction dredgers were deployed inside the circle to pump out millions of gallons of trapped seawater. Simultaneously, specialized transport ships filled the dry internal core with a custom-engineered matrix of non-shifting sand, gravel, and high-density liquid concrete. This rapid method allowed an entire rock-solid artificial island to be established in just a few weeks rather than multiple years, creating a perfectly stable structural platform capable of surviving Category 5 typhoons and providing a safe dry ramp for vehicles entering the underwater tunnel. 5. Stepping into the deep-sea submerged immersed tunnel system. Once a vehicle moves down the artificial island ramp, it transitions directly into the true engineering crown jewel of the entire mega project, the multi-kilometer immersed deep-sea tunnel system. Unlike traditional tunnels that are bored deep underneath the earth using massive rotating tunnel boring machines, an immersed tunnel is constructed by prefabricating giant, hollow concrete and steel tube elements on land, floating them out into the open sea, sinking them to the ocean floor, and locking them together underwater. Each individual tunnel element used in this project is a colossal masterpiece of engineering on its own, stretching over 180 meters in length, 38 meters wide, and 11 meters high. A single segment weighs approximately 80,000 tons, roughly equivalent to the weight of a full-scale aircraft carrier. These segments were manufactured inside the world's most advanced, fully automated dry dock factory facility. Because the tunnel sits under immense deep-sea hydrostatic pressure, the concrete had to be completely flawless. Even a microcrack thinner than a human hair would allow high-pressure saltwater to seep in, eventually corroding the steel skeleton and causing a catastrophic structural failure. To prevent this, the factory used an automated thermal monitoring system that regulated the temperature of the concrete as it cured, preventing any internal stress fractures from forming. Once a segment was fully cured and sealed at both ends, with temporary steel bulkheads, the dry dock was flooded. The massive 80,000-ton concrete block became buoyant and was gently towed out into the open ocean using a specialized twin-hull catamaran barge. Sinking this massive structure 40 meters down to the deep ocean floor through powerful, unpredictable cross-currents required an extraordinary level of technological precision. Standard ropes and anchors were useless against the momentum of an 80,000-ton block. Engineers utilized a network of deep-water acoustic positioning sensors, high-precision underwater sonar arrays, and specialized laser guidance systems to control the descent. The segment had to be aligned with the previously installed segment with an accuracy margin of less than 5 millimeters. Once the segment neared its target location on the pre-prepared seabed gravel bed, massive internal hydraulic winches slowly pulled the new segment tightly against the preceding tube. This action compressed a specialized, highly secret structural rubber gasket known as a Gina seal. Once the initial seal was made, valves inside the tunnel were opened to drain the small amount of water trapped between the two temporary bulkheads. The natural, crushing hydrostatic pressure of the deep ocean then pushed against the outer end of the new segment with millions of tons of force, permanently locking the joint and rendering it entirely watertight without requiring a single manual weld underwater. 6. Smart ultra-modern nano-coatings and environmental materials. Beyond the sheer mechanical scale and automated construction, what truly separates this project from any other infrastructure project built worldwide is its heavy reliance on next-generation material science and smart digital technology. The marine environment is incredibly hostile to standard engineering infrastructure. Constant exposure to high salinity seawater causes rapid oxidation of steel reinforcements, while marine organisms like barnacles and acid-secreting bacteria slowly dissolve traditional concrete, leading to rapid degradation within a few decades. To guarantee an unprecedented operational service life of over 120 years without requiring major structural maintenance, materials scientists developed a brand new, highly classified ultra-high-performance concrete alloy. This mixture is infused with specialized synthetic microfibers and volcanic pozzolanic agents that alter the concrete's molecular structure, reducing its porosity to near zero. Furthermore, every single piece of exposed steel truss and internal reinforcement bar was treated with an advanced graphene-based anti-corrosion nano-coating. This nanomaterial coating creates a flawless, atom-thick barrier that prevents moisture and destructive chloride ions from interacting with the underlying metal, completely halting the rust process before it can ever begin. The interior of the deep-sea tunnel is equally futuristic, running on an intelligent, fully automated central operating brain driven by cloud-based AI algorithms. Thousands of high-precision smart sensors are embedded throughout the concrete walls, monitoring structural stress, seismic shifting, water salinity levels, and air composition every millisecond. If a microscopic fracture begins to form or a minor shift occurs due to tectonic activity, the network instantly pinpoints the exact global positioning coordinates and transmits data to automated robotic maintenance crews. The tunnel's interior driving corridor features an adaptive, biometric LED lighting network. This system continuously monitors the external weather conditions on the open sea bridge and the exact time of day, automatically adjusting the color temperature and lumen output inside the tunnel. When transitioning from the bright, blinding sunlight of the sea bridge into the underwater environment, drivers usually experience a dangerous black hole effect where their eyes cannot adapt fast enough to the darkness. The smart lighting system completely eliminates this hazard by creating a highly graduated light transition zone, protecting drivers from eye strain and dramatically lowering accident rates in this critical infrastructure zone. 7. The engineering triumph, redefining the global metric for civil engineering. When this combined sea bridge and tunnel project was first conceptualized on paper, international civil engineering consortiums openly declared that the technology required to complete it safely did not exist. The sheer number of conflicting variables, from typhoons and earthquakes to deep-sea shipping routes and airport altitude restrictions, made it an equation that traditional construction methods could not solve. By inventing entirely new robotic machinery, mastering high-precision rapid artificial island deployment, and executing the most complex deep-sea immersion process ever attempted, the builders did not just connect two distant shores. They rewrote the international textbook on structural engineering. This 5,000-meter sea bridge and tunnel combination stands as an absolute monument to what humanity can accomplish when cutting-edge automation, revolutionary material science, and bold architectural vision converge seamlessly. It has successfully slashed regional transit times from several hours down to mere minutes, unlocking billions of dollars in economic potential while serving as a resilient blueprint for the smart, future-proof megastructures of tomorrow. The custom-engineered patents, automated shipping vessels, and robotic rovers birthed during this impossible build will undoubtedly guide global infrastructure initiatives for centuries to come, proving that with enough innovation, no barrier is truly unpassable. 8. China's ability to turn science fiction into concrete reality continues to push the absolute limits of human imagination and modern innovation. If you were blown away by the incredible engineering and deep-sea robotics behind this mega project, make sure to hit that like button and share your thoughts in the comments below. Don't forget to subscribe to NovaSpec and turn on all notifications so you never miss our deep dives into the world's most advanced, game-changing future technologies. Thank you so much for watching, and we will see you in the next video.